I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
Space. Time.
the brain,
Life. The universe.
Hello, this week is everything in the universe spinning. How does my dog keep fit despite spending the entire day apparently asleep? And is it safe to microwave plastics? Yes, we're answering the science questions that you've been sending in. My name's Chris Smith, and this is The Naked Scientist.
The Naked Scientist podcast is powered by ukfast.co.uk.
With me this week are Eleanor Drinkwater. Welcome back, Eleanor. Good to have you with us.
Hi.
Eleanor's a animal behavioural scientist. You work at the University of York, and you have brought in something animalistic.
Yes, I have. I have brought in a photo of the most adorable creature on the planet, which many of you may not realise is actually the woodlouse. So if you flip over a woodlouse, on its underside, when they are pregnant, the female actually has a pouch in which it will hold its babies before giving birth to them, a little bit like a tiny, tiny wombat.
And you can see this, can you?
Yes. So as you guys can see...
Oh, you brought a picture. Can I have a look?
have,
Can I
yes.
see this?
There we go.
This is a huge woodlouse. This has been inflated. This has blown up probably about 20 times, 50 times maybe. This is a huge snip. But no, you're quite right. So yes, there's a little pouch on the underside between the front legs, and there's lots of they look like little white maggots, but those are the babies.
Yes, they are.
How long will they do that for?
It probably depends on the species, but they wait until they have their first molt, and so then they're big enough that they won't dry out as soon as they hit the outside environment.
And then they eject the babies and they have to fend for themselves.
Yes, although they usually kind of stay near the adults because the babies actually enjoy eating the adults' poo.
Oh, I thought you were going to say enjoy eating the adults.
I think they'd be
Until they get
hard-pressed to
older,
do
it's a
that.
bit like teenagers, then they start sort of devouring their parents' bank balance, in my experience. Eleanor, welcome to the programme. Good to have you with us. Also here, Carolyn Crawford, who's an astronomer at Cambridge University's Institute of Astronomy. And you've brought in something for us to see virtually.
Well, virtual. It's a do-it-yourself show and tell. I bring you two planets, but you have to go and look for them in the night sky. And it's just a really good time to remind people what's up in the night sky, especially in the Northern Hemisphere. You've got the winter, it's dark late and it's dark early in the afternoons and in the mornings. When you're going home and it's dark, look for Mars in the night sky over towards the southwest. It's brilliant, it's red, it's low down the horizon. It's really bright, you can't miss it. And it'll be up till about 11 o'clock at night. And then in the mornings, if you're a relatively early riser, for about 3 hours before the sun rises, you can see Venus. And you can't miss Venus. Apart from the moon, it's the brightest thing in the night sky. Low down towards the southeast direction. So you can see Mars and you can see Venus at either edge of the night. And just one more thing, my favourite meteor shower is coming up. It's the Geminids. They peak, probably not for a couple of weeks, 13th, 14th of December, but I love this one. It's quite predictable. Go out late at night, preferably after the half moon's gone down, and you begin to see them. They peak around 2 o'clock in the morning, but you don't have to stay up that late. You can start to see them really towards after about 9 o'clock at night. And the thing about these is they're reliable, and when the meteors come, they're quite slow and they're quite bright, and so you can't miss them. So that's coming to a sky near you very soon.
Do they correspond to a cloud of dust that's just in our patch of the solar system, so that as the Earth goes around on its orbit, it sort of sweeps through that cloud of dust, and that's why we see them every year at this time?
Yeah, well, this is a particular trail of debris that's left behind a little asteroid called 3200 Pantheon. It's sort of disintegrating, and it's got this cloud that's followed its orbit, and every year we go through it on the same time of year, and then you get all these little bits of grit falling into the atmosphere and just producing these wonderful shooting stars, and it's all happening about 100 kilometres up.
Wonderful. Carolyn, thank you. Welcome to the programme as well. Sitting next to Carolyn, Patrick Short, who's a geneticist from the Wellcome Sanger Institute. He also is the CEO of a startup which is called Heterogeneous. Interesting name for a genetics startup. What does it do?
So it helps people learn more about their genetics and health, and also gives them greater control over their data. So it allows them to control who gets to access it and what it's used for, which is missing.
It's gone up the agenda a lot, data security, hasn't it?
That's right.
Especially genetic data
Yes.
and personal data. When did it start, the company?
About a year and a half ago.
And how does it make money?
So researchers use this data for all sorts of purposes. And actually, there are a lot of companies already that sell people's data. They just don't realize it. So what we do instead is allow people to sell it on their own terms or to participate for free. If they already have a disorder, for instance, a lot of patients are mainly keen to get their data out there so it can be used and get closer to a cure.
I thought Facebook had the angle on this.
And they're certainly trying, so are Google and everyone else, but we're hoping we can give people a little more control.
Welcome, Patrick. Have you brought anything with you?
I did. I brought a little stuffed animal, actually, which, like the woodlouse from earlier,
Is that your mascot?
Is blown up. It's not our mascot. Maybe it should be. It's a water bear. The scientific name is a tardigrade. That's right. And I brought it because it actually is one of the things that got me really excited about biology in the first place. So this little animal can survive radioactive bombs. It can survive being dried out and frozen and heated up to thousands of degrees. No matter what you throw at it, basically, it still survives. So I always thought it was quite amazing that an animal has figured out how to survive such extremes. So I think we're still, from a genetics perspective, trying to figure out how it does all these things. But it's quite a cool little creature.
They've flown in space, haven't they, tardigrades?
Oh, yes, they're incredibly robust.
Amazing. And last but not least, Liliana Fruch is from Cambridge University. She's a chemist and she has a penchant for nanotech and biotechnology as well. And you have got an array of tubes. You've brought in a stereotypical chemist's rack of tubes. What's in there?
I thought I need to show what the chemists are still about, and we are still about tubes. So I do have a selection of some of my nanomaterials that we prepared in the lab. So I have carbon nanodiamonds that get really people excited all the time. I mention, but they don't. Yeah, but unfortunately, they look like a grey powder.
So that will come in handy if you've got a nano girlfriend, won't it?
Yeah.
A nano engagement ring.
I mean, can you just imagine how wonderful that would be? Because it's actually made.
I don't want to rain on your parade or anything, Liliana, but this just looks like you poured some milk in a tube, if I'm being honest, and you diluted the milk a bit. It looks like half-off milk. What is this?
It's all about the story. Eh? How are you telling the story?
It better be, because this is not inspiring.
But if I tell you that these nanodiamonds were made in a huge explosion in a special chamber, and they are used for biosensing of small parts of the cells, then you would be a little bit more impressed.
Well, how did you make them then?
So we actually buy them from the company that makes them in the big explosion chambers. But what we do, we modify their surfaces. So we need to make them stable and adjustable to enter the cells. So, it's lots of chemistry out there.
Thank you, Liliana. Now, before we dive into the questions for our panel, we've got a quiz running throughout the programme. We did this on our last Q&A show, and congratulations if you did cotton on to the fact that our mystery creature that time was an ostrich. Can you, meanwhile, tell us what this week's creature is? Here's one of the sounds it makes. Give you some more clues as we go through the programme. Right, let's get into the questions. And up first, we have a question for you, Carolyn. Paul is on the line. Hello, Paul.
Hi there, Chris. Hi.
And you're in London?
Yes, I am.
What would you like to ask Carolyn?
If Earth was close to a big gravitational wave-causing event and somehow survived the actual blast, what would the gravitational wave feel like?
Carolyn, what do you think?
Oh, very good question. So if you are near a big event, well, we'll worry about how close in a minute, but let's work out what a gravitational wave does to you. And the thing about a gravitational wave is that these are travelling disturbances in the shape of space. They stretch and they squeeze space and everything in it. So if I'm facing an incoming gravitational wave, and imagine I stretch my arms out, I'm going to be stretched and squeezed alternately from one fingertip to the other tip, while being squeezed and stretched in the opposite direction from the top of my head to the tip of my toes. So I've got that action going on, stretching and squeezing. And there's also another mode which will stretch and squeeze me from my shoulder to the opposite hip, and then from the other shoulder to the opposite hip. So you are being shaken internally like a jelly. You're sort of being wobbled in all these different directions. However, this is happening to all of us all the time, right? And you're not feeling it, are you? Right? No. And this is because these gravitational waves, most of them are incredibly weak. I mean, the kind of length you get stretched. Well, we had the first detection was two 30 solar mass black holes that collided with each other a billion light years away. And that's one of the best detections we've had so far, the most sensitive detectors. And that stretched and squeezed a 4-kilometre-long laser by a distance less than a millionth of an atom. Okay, so gravitational waves are very weak. So then, but Paul was very clever. He said, what if you're close to a gravitational wave event? And magically, we're somehow protected to whatever is whether these black holes are colliding. Then it starts to get a bit more interesting because gravitational waves, well, how much you get stretched and squeezed depends on 1 over the distance. So if you had an event like 230 solar mass black holes colliding somewhere where the sun is, so 150 million kilometres away, the amount of distortion you might feel is of the order of tens of nanometers. I don't know whether you'd feel that. So
My nanodiamonds might feel it because they're very small.
They're very small, but whether you might feel it in your body. So let's move the event a little bit closer, and maybe it's a few thousand kilometres away. Then the amount of distortion gets to be about 1 millimetre over the length of a body. Again, whether you feel that or not, it's really got to be a few hundred kilometres before you start in being stretched and squeezed over, sort of 180 centimetres or so by 1 centimetre. Now, I'm reckoning you would feel that. I also don't think it would be very good.
Yeah, it probably wouldn't be very good for you, would it?
No,
for your body to have that phenomenon.
Would your muscles stay attached to your bone? What would it do to the brain? And, the absolute last thing I haven't told you about is the frequency that these gravitational waves are doing, the stretching, the squeezing. This is on sub-millisecond timescales.
Because they travel at the speed of light, gravitational waves,
yes.
or thereabouts, don't they?
No, they travel at the speed of light.
And so therefore your body would be stretched and squeezed at the speed of light. So you probably wouldn't be, if it was going to squash and squeeze your brain at the speed of light, then it probably would mean you weren't aware of it.
No, the gravitational waves travel out from the disturbance at the speed of light. What I'm talking about is the old, between the stretching and squishing. That would be you stretch and squish on basis of, less than sub-millimetre seconds. So I don't think your body would really survive that. So I think the answer to your question is you would be wobbled like a jelly, shaken from the inside out, and I don't think it would be very good news.
So, Paul, it would be a once-in-a-lifetime experience, I think, is what Carolyn's saying.
I still want to do it, though.
I think we'll leave that experiment out.
Paul,
Yeah.
thank you very much for your call. Now, Katie's popped in because you've got a question for Liliana.
I have, and it's about food. Is it really safe to cook food in plastic, like the plastic films you get on microwavable meals, or if I'm dinging my leftover curry in a plastic tub in the microwave? Or am I in danger of getting plastic leaching into my dinner?
Before I go into this question, we have to say that plastic is basically a common name for a large group of polymers, and they're all a little bit different. So in a chemistry lab, we'll use these polyethylene containers, which are really inert, and they don't have any kind of additives that will leach. They're very stable. But of course, if you have a food containers or bottles or even some of the foils that you use for microwavable food, they're made of different polymers. One is polycarbonate. It's kind of this transparent material. And to make this polycarbonate, you usually need to use other additives, small chemical additives in the process.
They're called plasticizers,
like
aren't
plasticizers. So they're embedded in the polymer, but some of them will be staying there. And so if you heat up the polymer, they can leach out. And one of these, and you might have heard of this, is bisphenol A, which is now kind of on the list of banned substances. And you will find also lots of materials which are free of bisphenol A. But this didn't solve a problem because now you have other additives that might have a similar effect. And this effect is that they disrupt our hormone cascades. So, our emotions are controlled with hormones. So this bisphenol A will basically mimic the hormones and activate them. So it's called endocrine disruptor. So if you have too much of this in your food, it's of course not very good. So the answer is yes, you might get something, but of course it depends on the type of container and material.
Eleanor?
Is there any way of knowing which one I can cook my food in and which one I can't? Or
But usually you will have the notice on the bottom if you check, and it tells you safe to heat. It's not that we are given something that is not controlled. There are some safe amounts of these chemicals that can enter the food chain, and they usually do. We continuously get stuff, and our body can deal with it. It's just that, yes, there are possibilities that if you have a particular food that might react with some of these compounds, you might get some side products. So I would microwave my things in the glass dishes if I have to, for example.
With that, Katie?
I think I'm going to go home and rearrange my kitchen. Yeah.
The precautions are taken so that, the things are under control. So I wouldn't throw all of my Tupperware out.
I'm reassured now.
Yes.
Thank you, Liliana.
the effects of sibling aggression can be more significant than we once thought.
100 electrodes to link my nervous system with a computer and then onto the internet.
The Naked Neuroscience podcast explores the workings of the brain and the nervous system in our bodies and beyond.
That sticks and stones may break your bones, but words and neglect might hurt your brain.
So you've got the little brain slice in the recording chamber.
From unravelling Alzheimer's disease to digging into dreams, join me, Katie Haylor, each month as we make connections with scientists around the world and spark up conversations on the latest neuroscience news. You can listen and download for free at nakedscientist.com/neuroscience or subscribe to Naked Neuroscience wherever you get your podcasts.
Still on the way, how do lazy dogs nevertheless remain in tip-top condition? And why is there so much more variety between dog breeds than there are between cat breeds? And also, does Ireland have more than its fair share of genetic conditions? We'll find out. Here's the second clue to our Who Am I quiz that we're running this week. We give you sounds and various clues as to the identity of a mystery animal. We played you one of the sounds it makes. Now I'm going to tell you that the males of this species tend to have more than one special someone. In other words, they're polygamous. More clues coming up in a minute. Ellen, a question here from Paul, who says on our forum, that's nakedscientist.com/forum. He says, how do earthworms move? Surely they're not strong enough to push dirt or soil out of their way, so how do they move around in highly compacted soil?
Well, this is a brilliant question. And if you think about it, how does this little blob of pink kind of manage to wiggle its way through such hard earth? And the answer is it's all about fluids. So if you've ever had a water balloon and you grab one end, the other end kind of shoots out. And that's kind of what's going on in worms. So if you look really carefully, you'll see that they're segmented all the way down their bodies. It has two sets of muscles, one that'll make the segment kind of long and thin, and the other one will make it short and fat. And so it's a kind of combination of these muscles working interchangeably, changing the shape of the segment without changing the volume of the segment.
So you've got a muscle that goes, or muscles that go along the length of the worm, and when they contract, they make it short and fat, versus muscles that are in rings around the worm, making it get thinner and longer when they squeeze.
In principle, yes.
And it's using the antagonistic effects of those two to change its shape. But how does that push a tiny worm through soil?
It's a bit like an accordion, the way that they all kind of contract together and space out. And it's just incredible, though, to think about the fact that each segment in this worm can move and contract independently. I just think it's mind-blowing, personally. It's amazing.
But don't they eat their way through the soil as well? I lived in Sydney, and these people introduced me to their wormery and said, we put all our household rubbish on this and they turn out worm juice. And this is plant magic. This is like gold dust for plants. It makes everything grow.
Yeah, they do eat vegetation in the soil, but they can also wheel through it as well.
Liliana?
Yeah, I just wanted to say I'm never going to look at the earthworms with the same eyes any longer.
If you go into my garden, I've taken to burying all of my kitchen scraps. Not the meaty bits, because you'll attract loads of rodents, but all the vegetable waste I now rebury because it does attract worms, and they do have an enormous role in soil improvement, don't they? Because by making these holes that Paul is referring to, they actually improve the drainage of the soil, but they also, turn over all these things and move various nutrients up and down in the soil, which is a good ecosystem service as well.
Yeah, definitely. They're unsung heroes of the garden.
Well, look, this is an amazing link, this one. Carolyn, I'm looking at you. You can probably guess where this is going, can't you? Because we've been talking about worms. Now we're going to talk about wormholes. Oh. Sorry. Also on the forum, Wannabe Astronomer says, since we don't know what's past the event horizon of a black hole, could a black hole be a wormhole? Or would it just kill you and add you to its mass in its centre? Could you just explain what all these words mean? Wormhole, black hole, event horizon.
The event horizon is, if you like, the horizon beyond which you can't detect any event. So it's the invisible boundary around a black hole. It's the point of no return. Like if you step over that, yes, the short answer is you get killed, you come part of the black hole. But the trouble is that no information can cross from the inside of the event horizon to the outside. So as the questioner says, we don't know what goes on inside the event horizon. What we suspect is there's lots of empty space, and right at the centre you've got what's called the singularity. It's the black hole itself. It's infinite mass crushed down to tiny, tiny volume. There are ideas that say your black hole is rotating and maybe the singularity gets stretched out into a ribbon. It would be possible to cross over the event horizon. perhaps fall through and avoid becoming part of the black hole, and perhaps pass through something called a wormhole, which is like a tunnel through to elsewhere or elsewhen in the universe, and get spat out in the opposite of a black hole, which is a white hole. So you have this idea, you fall into the black hole, go through the wormhole, get spat out as a white hole. Now, all of this, if you look at the maths, is okay. If you look at Einstein's equations, they can predict black holes. They'll also produce white holes. The only snag about white holes is you have to wind time backwards rather than forwards. So it's a bit of a snag for them actually existing. And also, we see black holes everywhere in our galaxy. Everywhere in the universe, we don't ever see a white hole. So then you've got to start questioning whether wormholes exist. Now, they're a really nice idea. You see them in science fiction books and movies, how you get around the universe or how you travel in time. In practice, when you look at the equations, and I'm simplifying grossly here, they're very unstable. You put a toe in a wormhole and it will just collapse around you. So I don't think it's a good way of getting around the universe. So the answer, we go back to the fact that, if you go over the event horizon, I think you're going to become part of the black hole. It's going to kill you, in fairly dramatic ways. Just to remind everyone, a black hole, despite the name, is not a hole in space. It's a thing. It is, an area of extreme mass, extreme gravity, and you would just add to that mass and gravity.
Well, let's come back down to Earth for a moment. And Eleanor, got this question from James, who got in touch on Facebook, and he says, how do animals, like domestic dogs, maintain their muscles and fitness when they seem to do relatively little? In the case of the dog, my mum's dog, it does absolutely nothing, in fact, but it can still run really fast. And he says, our dog does minimal exercise during the day, apart from its 30 to 60 minute walk. But when we go to the beach, it can run around without tiring itself out. Humans, on the other hand, seem unable to run tirelessly without appropriate regular training. What's the dog's secret?
If you think about it, a lot of breeds of dogs are built for speed. So something like a greyhound can hit about 45 miles an hour. So even an unfit greyhound can still be much more speedy than the average or relatively fit human. And, like humans, with more exercise, dogs become more fit. And with less exercise, they can also become more fat. But on a wider level, how do animals in general stay fit? There are some amazing adaptations out there. I mean, two of my favourite examples are something like barnacled geese. When they're preparing to fly really long distances, they only need a couple of minutes of flight a day to build up enough muscle in order to become fit enough to migrate, which I just find crazy and so unfair. And then on the other hand, you have some animals that do this amazing trade-off in how fat they are versus how thin they are, depending on predators. So a good example of this is porpoises around the UK. If they're in areas in which they are at risk of being killed by dolphins, they tend to be much more sleek and much able to get away from dolphins than in areas in which there are less dolphins. So basically, the animal kingdom is brilliant and there are loads of interesting adaptations to fitness.
So they basically evolved in order to endow themselves with the ability to do that because it's beneficial to them to do that. And were it not beneficial for them to maintain this, I guess that's probably because we keep opening the tin of dog food, isn't it? I mean, if we didn't keep feeding them, they would lose condition. And the fact that they can afford to maintain all this muscle bulk, which is energetically very costly to maintain all those muscles and things that they're not using. We, on the other hand, as humans, we just sort of run to fat if we don't take regular exercise.
Yeah, we have quite a sedentary lifestyle compared to most species of animal.
Liliana?
Yeah, I just looked at Patrick and I told him blame it all on DNA.
Now you're being made the butt of this.
Well, I was going to say that we humans probably spend most of our energy keeping our brain intact, right? That we don't have to do much to train it and it will still do most of the essential functions. So maybe the dog's spending less time training its brain and more on the muscles.
It's an energetically very costly organ, the brain, isn't it? You think it's running at roughly 20 watts because it's about 20% of your oxygen consumption, and your average person's running at about 100 watt. It's about 1 or 2 watt per kilo in the average person. So your brain is burning a lot of energy.
Yeah, and in some cases, like for example, sponges, people thought that there's some evidence to suggest that they had a neural system or even kind of a brain-like structure, but because it's too energetically costly, they've got rid of it. So, we don't need a brain.
I know a few politicians that actually might fit that bill. Now, Patrick, let's skip over the water from England to Ireland. We've got this question from Dee for you.
Ireland has significantly higher rates of multiple sclerosis and cystic fibrosis compared to the rest of Europe. How does that happen? We can't be that different to the rest of Europe, right?
Dee's absolutely right. There are some hotspots in Ireland for various genetic conditions. Another one is celiac disease, isn't it? Galway in Ireland, I think, has the highest concentration of people with celiac, and that has a genetic linkage as well.
Yeah, absolutely. It's a very good question. And this is also the case, for example, in places like Finland, as well as many Greek islands or other places, anywhere where you've had, at least in the past, some kind of either relative isolation or else a big population bottleneck. If you had a small number of people that go and colonize a place to begin with, then the amount of genetic variation that went into that colonizing event means that certain disorders that may have been relatively rare to begin with just happen to end up being common. So the example I'm most familiar with is Finland, but I think it probably applies in Ireland as well. But if only about 2,000 people colonized the country some tens of thousands of years ago, then if one or two of those people had a particular disorder, then as that population expands, it can be at quite a high prevalence. And also the existence of any kind of clan structures or mating structures that mean people are more likely to mate with one another can cause these to increase further still.
So is that also the case for Iceland? Because I have read that that's quite a closed gene pool, isn't it? And it's of great interest to researchers for that reason. Do they also have this issue about these diseases?
Yeah, so the genetics research that goes on in Iceland is quite amazing. They're very soon going to genome sequence the entire population. They also have genealogical records going back for many generations, but I believe it is the case there as well that there's a number of disorders that are at particularly high prevalence that are specific research priorities for that country.
Is it worth considering also that these genes that we regard as disadvantageous under certain circumstances, the reason they might be in those populations and have risen to such a high prevalence could be because in the past one other function of those genes is to confer some kind of advantage under certain circumstances, and therefore they've become concentrated in the population. And while they're disadvantageous if you have the right environment, they're advantageous under other conditions.
Yes, that's absolutely right. One of the best examples of this is the gene that causes sickle cell anemia that also confers a resistance to malaria. So you can, if you have two copies of the gene of the mutation, then you're likely to have sickle cell. But if you have one, it's actually protective from malaria. So you end up with this balance. But in places in the world where malaria is not an issue, then it's often at much lower prevalence. And there's lots of other great examples.
I was thinking specifically one of the diseases that Dee mentions in her question is cystic fibrosis. And we've learned in recent years that the gene that is linked to cystic fibrosis happens to also confer resistance to certain salmonella infections. And so we think that's one of the reasons why that gene is so common in the population, because people would have had some degree of resistance against typhoid, for example, historically. So it became more concentrated in the population.
Yes, the other interesting thing about cystic fibrosis, there's a single mutation that accounts for a large fraction of the cases. There are all sorts of mutations that can cause it, but whenever there's a single mutation that's very common, it's often can depend on the frequency within a particular population, how frequent the disease is in general. So probably that Delta 508 mutation that's quite prevalent in cystic fibrosis happens to be very common in Ireland for reasons that we may or may not have figured out yet.
Thank you, Patrick. Here's some more clues to our what am I or who am I. We told you what it sounds like. We told you they're polygamous. The other clue is there are two subspecies of this particular creature, and one, rather flatteringly, has got the name Superb.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Right, quiz time, everybody. What basically we've got is two teams, and that's going to be Patrick and Carolyn on Team 1 and Liliana and Eleanor on Team 2, and it's going to be the Biggest Brain of the Week award. Okay, are you ready? So you can confer, of course, and we'll go in the team order. So the first one, this is round 1. This is called A Matter of Time, this round. So, Carolyn and Patrick, which can live longer, a shark or a tortoise?
Are we allowed to confer on air? He's whispering at me.
I was whispering.
We tend to think it's going to be a tortoise.
But maybe he's tricking us.
Yeah, and sharks also live pretty long. But
Yeah.
I think I'm going to go for the tortoise, because there's one that lived over a century, isn't it? One of Darwin's tortoises.
Yes.
died in...
I'm with you on that.
Yeah.
So you're going to go tortoise?
Well, giant tortoise.
Giant
Very
tortoise.
specific.
There we go.
They're very long-lived,
Not
giant
just any
tortoises.
tortoise.
Yes.
I knew he was tricking us.
No, by carbon dating the eyeballs from dead specimens, scientists recently showed that Greenland sharks live for more than 400 years. Female Greenland sharks are estimated to be at least 150 before they begin to reproduce. Now, you're quite right about the tortoises, though, Carolyn, because in the wild, giant tortoises do have a long lifespan. It's at least 100 years or more. And in 2016, Jonathan, the giant tortoise in the Seychelles, St Helena, was said to be the oldest living animal. He was more than 180 years old.
Yeah.
So you didn't get any marks, but you did show good knowledge. So it's a good start. But, you can do a bit of improvement in round 2. Team 2, this is Liliana and Eleanor. Which lasts longer, a day on Mars or a day on Venus? What do you think?
Can we answer the shark question instead?
Anyone would think we decided which questions to put to who.
Wait. Day on Mars. Because it has...
Day on Mars or a day on Venus? Which
one's
longer?
bigger?
Which
right?
one is the longer?
I mean...
Well, that's the question, Eleanor. That's what you...
Is it the distance?
Well, I've not got...
I go with the day on Mars.
I like your definite.
Yes, I am.
Yeah, I trust you. You seem confident in this.
Yes. Caroline is waiting.
Oh no!
Caroline, why are they wrong?
Because a day on Venus lasts longer than its year. So Venus goes once around in about 240 odd Earth days, which is longer than it takes to go once around the sun, which is 225 days.
Oh my goodness.
And a sol, a Martian day we call a sol, that's about the same length. It's within, I don't know, half an hour or something is the day on Earth.
Yes. Oh, I kind of thought that Venus.
Thank you, Caroline. I now don't have to read the answer, which is saves a bit of Round 2, Animal Magic. Team 1, Patrick and Caroline. Which of these unattractive sounding animals is real and which one did we make up? Or are they both made up? The scrotum water frog or the bloated flatfish? What do you think?
Don't look at me.
Man,
I'm sure somewhere in the universe there are planets where both exist, you know. So you can't tell me unambiguously that none of them exist.
So we have the scrotum water frog.
And
is that what you said? And the bloated flatfish.
Yes.
Man, you just wanted me to say those on air, didn't you?
Yeah, I think bloated flatfish doesn't sound total stretch of the imagination.
Yeah, but maybe he's trying to trick us again. He's
We'll take that as
one.
assumed, yes, but it could be a double bluff.
It could be.
What are you thinking then? You're going to go with the frog or the fish?
Let's go with. Well, what do you think?
I would go with the fish, but I'm not an expert
Fish
in this.
is real. Okay, let's.
So frogs.
Yeah, let's say the frog is not real. The fish is real.
You're going with the frog is made up.
Yes.
Yes, knew it.
They both made up.
No, the scrotum water frog lives in Lake Titicaca in the Andes. It's evolved a reduced lung capacity and is compensated by having very highly convoluted skin folds. I don't know why I'm looking at you, Eleanor. You're the biologist in the room. And these convoluted skin folds help it to breathe, hence its name. And apparently these frogs do press-ups on the bottom of a lake, and that creates disturbances in the water. This increases the delivery of oxygen, which it then absorbs through its skin. You're doing very well, that team. You've got 0 so far. Okay, back to team 2. See if you can improve on the score of 0 overall so far. So, Eleanor and Liliana, true or false? Cats lack the ability to taste anything sweet.
That's true. That's totally true.
Yeah, I would go with Eleanor.
Because they did an experiment on lions in which they gave them the choice of water with sugar or water without sugar, and apparently they couldn't tell the difference, or they behave similarly to both, and so it's kind of... So they assumed that they can't taste sweet. The similar question, which hasn't been tested, which I'm dying to test, but no one's let me do it yet. Can penguins taste fish? That's another question. No one knows.
But lion bars taste sweet.
What? Lion bar? I think that might be a bit different.
So you're going for the actually that's true. Cats can't taste sweet stuff.
Yep. I'm going to be really embarrassed.
I'm very lucky to have Eleanor on my team.
You're off the bottom. Yes, you've got 1 point. It's true. There are 2 genes which are used to make a working sweetness detector, which is on the tongue. Cats lack a working version of one of them, so they can't tell sweet from non-sweet, despite experiments like the ones you outlined there, Eleanor, where people have tried to get them to discriminate between sweet and non-sweet things, and they can't do it. There you go. Very well done. Back to team 1. You've got to save your rep here. It's all on this one. So this is called Solve This round. This is a riddle / a thought experiment, which you've got to work out what the answer to this is. A cork dropped into a glass of water always drifts off to the side. So how can you make sure that the cork will always float in the centre of the glass? And to solve this riddle, you only need glass, water and cork. What are you thinking?
Do you have any of the Jeopardy music while we think?
Yes. Do you have a cork? We could quickly experiment here.
So it always drifts to the side.
How about you stir up the water before you drop the cork in, and then you're not going to get motion out to the side of the glass?
No spoon provided, no fingers, just water.
No fingers.
Yeah.
You've taken our fingers.
How are we going to drop the cork in then?
With your mouth. No mouth? No, I don't know. That's not the answer I was thinking. It's a good idea, but it's not the right answer.
I can't drink the water and then it'll...
It's got to float.
Is it a normal glass, or can we change the shape of the glass in any way?
No, you get the same glass.
Right. This is quite a conundrum.
Yes.
I'm going to have to hurry you. Do you know the answer?
No.
I'm going to have to give you a wah.
Give us the wah.
Fine.
We deserve it.
The answer is, right, that you fill the glass right to the brim, because think about it, the surface tension means you'll pull the water into a curve. The cork always floats to the highest point in the water, and the reason it goes off to the edge is because normally the water forms what's called a meniscus, where the edge of the water is higher than the curved surface, which is why the cork goes there. Because of surface tension, you can overfill the glass so it bulges above the rim, and the cork will float to the top dead centre in the glass that way. So that was the answer.
Pretty clever.
Yeah, I'm glad you appreciate that. It's lovely. Right, no marks for you then. Right, you could be clinching it by the looks of things. Do you want to have a go anyway? It's quite fun, this one, isn't it? So, Eleanor and Liliana, this is purely just to show off now. If you balanced a mop horizontally in your finger and you then cut the handle at the point where it was resting on your finger, so you effectively get two bits. You get a long bit of handle and then the short bit of handle with the mop head. Are you with me? So you've got the mop resting across your hand. If you weighed the two pieces, the short bit and the long bit, which would weigh more, the long bit or the short bit, or would they weigh the same?
If you can balance it.
If we can balance them.
I would guess it would be the same. I feel like this is a trick question. This is a sneaky question. You want us to say the same, but I don't think it is. What's the mop made of?
It's a normal mop.
Okay. Oh my goodness.
What do you think? Mop. Which, are you going to say they weigh the same?
No, it can't be the same because that's too easy.
Going to have to hurry you?
I don't know. Maybe we should just go same. Okay.
Probably fail.
Unfortunately, you lost your edge right at the end. So what do you think? You got an answer, Patrick?
Well, the mop head is going to be heavier and it's further out, right? So you've got to have the other side's going to weigh more.
I'd love to give you a bonus mark and let you.
Do we tie in the end?
No, unfortunately, I'm not going to let you get away with that one. Otherwise, Carolyn would have clinched it for you earlier, wouldn't she? But the short bit actually weighs more, and this is why you have to put your finger so much closer to the mop head, because there's a leverage effect. If you think about the length of the handle, it's much lighter, the long handle, but because it's acting over a long distance, there's a bigger torque. So it will actually weigh a lot less, but it has a longer leverage. It's like Archimedes said, if you give me a lever long enough and a place far enough away to stand, I could lift the earth. And that's the same principle. So actually, it's a trick. It wouldn't weigh the same. The mop head plus a short bit of handle would actually weigh more. Okay. Just time to sneak in the last clue for our Who Am I quiz. We've already given you a whole range of different bits of information about this particular animal. We played you the sound they make. We told you they're called superb, and we told you they're polygamous. Eleanor, you do a lot of wildlifey things. Any idea what these might be?
Yes, can I say?
Well, shall I play you what they sound like? Still convinced you know what this is?
No, I've changed my mind. But
what were you thinking?
Well, the first sound that you played sounded a bit like a kookaburra, but that's definitely not a kookaburra. I do know what this animal is, but I can't remember the name off the top of my head, and my birder friends are going to murder me.
Anyone like to speculate?
A lyrebird?
Yes.
It is. It's the lesser spotted chainsaw lyrebird. No, but it was imitating a chainsaw there. But it is indeed a lyrebird. These are animals. They're native to the eastern states of Australia. They're two species. They're ground dwellers, and they are best known, as you say, Eleanor, for their superb ability to mimic. And they mimic both natural and artificial sounds in the environment. And this is why I'm looking at you, because the lyrebird sound that we played at the beginning was a lyrebird imitating a kookaburra.
The sneakies.
Yeah, so very, very sneaky. I should point out that Team 2, to give them their credit, did win the quiz. So you are this week's big brains of the week. So very well done to Eleanor and Liliana. I robbed you of your fame at the time. I do apologise. Very well done. Now, Carolyn, can you try and unravel this question from Sean for us? He's emailed in a bit of a spin, and he says, why is everything spinning in the universe? And if black holes are at the centres of galaxies and they're spinning very fast, are black holes breaking up nearby objects and ricocheting them away?
Well, let's leave black holes out of things for the minute, because yes, a lot of stuff is spinning in the universe, right on the scale of not just planets and moons and solar systems and stars, but also whole galaxies are spinning. And it's really a question of something called angular momentum. And this dictates, if you've got a body that's spinning, it's telling you what rate it's spinning in and what direction. And angular momentum is a conserved property. This means that once a body has got angular momentum, you can't get rid of it unless you kind of apply an external force. And the way angular momentum goes, if you have something that's very large, that is spinning just a little bit and it shrinks down, then it spins faster. So you've got this conservation. And the nice thing about astronomy in space, things in space are made from gravity. So you start with a big gas cloud, tiniest little tug, gravity to one side to the other, it's got a very lazy spin. But as it collapses down to form a star, or even on a big scale a galaxy, it starts spinning up faster and faster. So that's the basic reason why so much spins in the universe, because it's more likely the original gas cloud is going to have the tiniest torque on it than not. So when you get to black holes, we think every black hole spins because they form from massive stars, and massive stars are formed from these gas clouds. So if you have a star that's spinning, if it then collapses down to a black hole, it's going to spin even faster, and black holes can spin incredibly fast. So going back now to the original question, can they break up nearby objects? Well, they're going to break up nearby objects because of their gravity, not because of their spin. And as we discussed earlier, it's not very good if you go over the event horizon of a black hole, you get what's known as spaghettified. So things get broken up because of the gravity. They're going to get pulled onto the black hole. They're not really going to get ricocheted away.
In the quiz, there was the question that you answered for me about Venus. Mm-hmm. And you made the point that actually it's turning excruciatingly slowly, so a day is almost longer than a year. How did it end up going so slowly then?
Well, it's not just that. Venus is basically spinning at walking pace. Okay, the Earth spins at about 1,000 kilometres an hour. Venus is literally walking pace. Not just that, it's also going in the wrong direction. This is really cool.
Well, the sun rises in the west on Venus, doesn't it?
That's right, rises in the west, sets in the east. And so if you look down on all our solar system, the sun is spinning in one direction, or the planets are going around the sun in that direction, or the planets are spinning in that direction. It's just Venus that's going the wrong way. So we don't think it formed different from all the rest of the planets because we assume they just inherit the same rotational motion from the original kind of nebula that collapsed to form the sun and all the planets. There's something that's happened to Venus subsequently that has slowed down its rotation and even just turned it the other way. And it could be due to its really thick atmosphere. You've got the gravity of the sun creates what we call tidal bulges. It kind of pulls this thick atmosphere in the direction of the sun. And if that is rotating at a different rate than the planet underneath is rotating, friction between the atmosphere and the planet just slows it down. We've got the same effect on Earth, between the moon pulling the oceans around to form tides. That's breaking the Earth's rotation slightly every year. But on Venus, it's much more extreme. You've got this really dense atmosphere. And so that is probably the most likely reason for it to have been slowed down and then just slightly started spinning the other way.
But for the reason you've outlined, something else will have inherited that angular momentum from Venus, and something else will be spinning the equivalent amount, won't it?
Yeah, it could be. And it could well be transferred to the sun. So whatever is perhaps slowing down the angular momentum, if you treat Venus and the sun as a closed system, maybe it's going to spin the sun up slightly.
Thank you, Carolyn. Now, Patrick, over to you. Steph is wondering about identical twins. And Steph says, how come some identical twins still look kind of different? And I know what Steph means because, I went to school with some identical twins. And yes, it was a bit confusing to start with, but you begin to see very subtle differences. So we all got pretty good, teachers included, even though they did try to swap over from time to time, at telling who was who. So why are identical twins identical in the first place, and why are they subtly different at the same time?
Yeah, it's a great question. So twins have had a very special role in the history of genetics. They've helped define this concept of what we call heritability, which is basically how much does variation in genetics explain variation in a trait. They've helped define that for a huge number of disorders. In the early days, it was often identical twins that were compared to non-identical twins, which are basically like siblings, but that happen to be born at the same time. And so when you compare those two groups, you can basically say, okay, the identical twins have the exact same DNA with the exception of maybe a small number of mutations that one or the other might have, whereas the non-identical twins are basically like brothers and sisters, so they share half their DNA. And that allows you to calculate if a trait varies about the same amount in identical and non-identical twins, then it's probably not genetic at all. And if the identical twins are very close, it has more of a genetic basis. But what is often forgotten is almost every trait has an environmental component. Anything we can think of, whether it's cancer, cardiovascular disease, even our personality traits are molded by our environment. But there's a third factor, which is just randomness, or what we might call stochasticity. So even if you're studying a trait that you think has a huge genetic component to it, maybe face structure, for example, in the what people might think of as something identical twins should be very similar in, there is always an element of randomness in development. That means even if something is supposedly perfectly genetically tuned, which probably even facial development isn't, then there's an element of randomness that just means you're going to end up with differences over such a long process of many years of development.
So is a clue something like freckles or moles on a face? Because in my experience, that's been a way to identify between two twins.
I was thinking exactly that.
Yeah.
We could tell one of these two kids from the other at school because one had a mole and the other one didn't.
Is that an example of what you mean by this randomness?
Yeah, that's right. It could be something like freckles or moles that might represent a mutation in an individual skin cell. So that's what we call somatic mutation. So I'm not sure exactly how a mole arises, but freckles, for instance, have to do with the mutations that change the way pigment accumulates in the cell. But there are other, beyond just genetic changes on a cellular level, simply the morphology of your face, how every at some point you're a single cell, and then you're 2, and then you're 4, and then you're 8, and the way those cells move around and arrange and become your body and your face, it's impossible to program perfectly. There's a lot of great photos on the internet that if you take Obama's face and you kind of slice a line down the middle and copy the left side of the face across to the right, or if you do the same and copy the right across to the left, they look like completely different people. So even your left side and right side of your own face, if you were to duplicate it to the other side, you'd look completely different.
But a sheep can tell Obama apart, can't it? Researchers in the Babraham Institute showed that they can spot celebrities, can't they? And
yes.
One of the celebrities they used to show that sheep can recognise people was Obama's face. So reassuring to know they're doing very important research on sheep face recognition. Now, sticking with animals, and in fact, this one's about cats and dogs, Ellen, from you. Nearly P on the Naked Scientist forum. That's nakedscientist.com/forum. He wants to know, very pertinent observation is, why are there so many more varieties of domestic dogs than there are cats? And they vary so much, for instance, in size and shape as well, where you've got, say, a Chihuahua right up to sort of Irish Wolfhound scale differences in dogs, but you don't see that degree of difference in cats.
This is a really lovely question. And in fact, this has been an area of a bit of debate in biology, as some people have been suggesting that it might be that dogs are kind of special genetically, perhaps they mutate a bit quicker. But I'm afraid the kind of consensus at the moment is a little bit more boring, but still quite cool, is that it's because of us, and it's because of selective breeding. So if you think about what dogs have been bred for, so you have huskies who've been bred to pull sleds, or you've got, dogs who've been bred to hunt deer or go down rabbit holes. It's a real variety of things that they've been bred for. Whereas cats, perhaps they've been bred for not quite so many chores. I mean,
cats just won't cooperate with anything, will they, in my experience?
that could be
so that might be why.
Yeah, but I mean, if you look at something like horses, for example, something like a Shire horse who's been bred to carry huge loads, or like a Shetland pony, you kind of get a bit more of the same size dimorphism than you do in cats.
Thanks, Eleanor. So it's all in the breeding, and it's probably because cats are absolutely refuse to indulge in any kind of thing other than just using you as a slave and a food machine.
I think that's very sensible.
Probably by Patrick. You're the geneticist. You tell us. Is there a gene that explains why cats refuse to behave and do what they're told?
Someone should look for it. I'm familiar with how dogs became domesticated to some extent. There's, I suppose, some kind of cooperation between humans and wolves and ultimate domestication, but I don't know how cats became domesticated.
Do you think the Egyptians had something to do with it? Because they loved cats, didn't they? They thought they were very special.
They did, yeah. But did they? What was the original big cat that they took and made it into a small friendly cat?
Carolyn?
Do you not think it's cats domesticated us?
Oh, that's a good alternative take.
They certainly subjected us to servitude.
The cats do seem to think
I don't
that,
think
don't
we
they?
had much say in the matter here.
Liliana, a couple of questions for you. These both concern plastics. They're from Stephen on Facebook and from Ash. They say, I've been wondering lately about plastics in the environment. Biodegradable plastics for wrappers, etc., are seen as a way to reduce plastic, and they're seen as a good thing. But I'm wondering what chemicals end up going into the soil as the plastics break down. Is biodegradable plastic all good news, or is there a flip side? Ash wants to know, are people still making alternatives to plastic? So how viable are they for replacing the plastic that we're so hooked on? What do you think?
Yeah, so people are actually still working on all kinds of polymers, and biodegradable polymers are a big thing. And there are lots of procedures out there to turn some of the natural polymers, like cellulose is a natural polymer, or chitin.
Basically known as wood, isn't it?
It's like wood. Or chitin, which is present in the shell of shellfishes or insects, is also a polymer that has been used to make some biodegradable polymers as well. But I would like to point out here that maybe the biggest problem when we think about plastics, it's not design of biodegradable plastics in itself. Because the industry and also the applications of the plastics, the industry will always look for processes which are cheaper. And for now, we have plastics and polymers which are way cheaper than biodegradable plastics. So maybe instead of also only focusing on biodegradable plastics, we also need to focus on finding the ways, how do we recycle the plastics that we already have out there in the environment, and how can we reuse it for something else? And I think this is more a question of the policy than the science.
And this question about when these things break down,
yes,
what they break down into.
Yeah, well, the problem is, okay, biodegradable plastics, that will all depend what is it made of. And so polylactic acid, for example, is biodegradable. So it wouldn't be as terrible as one would imagine, but you would still have a very persisting big parts of plastics which might end up in the stomachs of animals and then go through the system. So it's, we are still not out there that we could definitely find a biodegradable replacement for the plastic that already exists.
It's a good point, though, isn't it? And something that in this era we need to focus on, finding things that we know will not just rob Peter to pay Paul, because it's easy to brush this particular plastic waste under the carpet, isn't it? Say, well, it's biodegradable now, but what it turns into is pretty important.
Exactly. So I think it's more focus should be done first on how do we deal with the plastic waste and our types of plastics that are already there. We are just not going to stop making them. And the second thing, could we maybe take cues from really biopolymers, like, as I said, cellulose and chitin, which have natural mechanisms of breaking down. So I think this will be two directions that science will focus in the future. And it's focusing now as well.
Thank you, Liliana. Emily's popped in, and you have a question for us. What would you like to talk about?
So my question is an astronomy question about light years. So as I understand it, a light year is the length of time it takes for light to travel. No, you're shaking your head already. Okay. If, say, something was 100 million light years away and someone or something had a telescope pointed at the Earth, does that mean that the images they'd be receiving from Earth 100 million light years away would be Earth 100 million years ago? So, for example, like if aliens were observing us, would they have completely the wrong end of the stick and think we were just like a planet of dinosaurs and be preparing wrong for invasion?
Yeah. Well, I'd love to see their telescope. They gave them that much detail of that distance. Yeah, you never know. Okay, well, I was just shaking my head when you started off, because even though it sounds like it ought to be a measure of time, a light year is a measure of distance. So it's how far light travels in 1 year. And we all know that light has a finite speed. Fastest thing there is. It travels at 300,000 kilometres per second. But that means in a year, it travels 9.5 million kilometres. And astronomers kind of get fed up saying millions and millions and millions. So we just stick to light years. So therefore, a light year is telling you a distance that it takes light to travel in 1 year. So going back to your question, you've got your aliens or whatever 100 million light years away. The light that they receive in their telescope that's come from the Earth has taken 100 million years to get to them. So they are just seeing the light that left Earth 100 million years ago. So they're seeing the Earth as it was 100 million years ago. So you're exactly right about that. And this is such a neat thing for astronomers, though, because it does mean that we can effectively look back in the past, because we can compare a galaxy that's 100 million light years away to a galaxy that's 6 billion light years away. And we're seeing the universe at different epochs. So it does work in our favour at times.
I did like your comment about preparing all wrong for invasion, though. That's the funniest way I've heard it put in a very long time. Thanks very much, Emily. That's a brilliant question. Now, Katie has just popped in with a very important update on our fundraiser.
That's right. We are trying to raise £50,000, and this is to keep The Naked Scientist going, as well as to develop some rather exciting programmes for next year.
Indeed, and we're going to give you a sneaky preview of some of what we're trying to cook up very soon.
Meanwhile, we're so pleased to tell you that so far we've raised just over £5,500.
And you are, as you're doing that, sending in some wonderful comments as well as your money. I just want to acknowledge, thank you very much to Keith, who said, "Thank you, Chris and the whole team, for a fantastic programme. It's always interesting and one of my few compulsory listening shows every episode." Thank you, Keith.
And this rather lovely comment from Francis, who says, "Who knew science podcasts could be so much fun?"
And high praise indeed from John here, who says, "We're the best science podcast there is, bar none."
And Richard says, "You guys do such an awesome job. I really enjoy listening to your podcasts as I run or drive. Keep it up." And we're glad to be with you on your journeys, Richard. So thank you very much.
And also Peter says, "Critical thinking is at the core of our human understanding, and The Naked Scientist promotes scientific critical thinking at every turn."
Thank you so much to everyone who's helping us out. So if you have a spare extra few pennies, why not consider giving us an early Christmas present? And if you've got an idea for a show that you'd like us to consider, you could let us know. It could not be easier to donate. nakedscientist.com/donate.
Well, there we must leave it for this week. But thank you to our guests, who are Patrick Short, Caroline Crawford, Liliana Frooke and Eleanor Drinkwater. Thank you to Katie, who put the programme together. And do be sure to join us again next week when we're going to be journeying through space and time to explore space travel. The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.